Good morning, everyone. I'm glad to see so many people here today. It's my great pleasure to present someone who most of you know, Jose, who's here at the IAC. He is one of the members of the science team for Planck, specializing in leading a group that's studying galaxy clusters. And I'm sure we're all going to be very interested to hear his talk about the early results of the Planck mission.
Hello. So good morning, everybody. Basically, what I'm going to present you in the next 45 minutes or 50 minutes is the outcome of the first years of observations with the Planck satellite. Basically, this outcome appears as a special issue in Astronomy and Astrophysics, which was published last December, and which contains basically 26 articles covering a large range of topics, basically related to galaxy clusters, radio sources, and the physics of the emission of our galaxy in the millimeter range and the submillimeter range. Probably most of you know what is Planck, because here at ASC in our CMB group, we have been working for many years, and during this year, you already had some presentations of what is expected from Planck and so on. So this thing is really becoming a reality. So I will try to go first quickly through what is Planck and what can we do with Planck, and then I will focus on this result I was mentioning. Planck is a third-generation CMB space experiment in the sense that we first started with COBE in '92, detecting the anisotropies, then WMAP in 2001, presented a more detailed picture, and Planck is going to basically give us the final picture from the point of view of temperature of what are the CMB anisotropies. The primary goal from Planck is to measure the CMB temperature anisotropy. You have here a comparison of what we expect to do in relation to WMAP. And if you translate that into the constraints of cosmological parameters, you see immediately that we have a huge improvement of a factor of practically 10 in some cases for the precision of the determination of the cosmological parameters. This is the primary goal of Planck, but today I'm not going to talk about this, because this is the science that will be released basically in 1 year from now. But the other science that Planck can do, and is the topic of the talk today, is what science can we do with observations in the millimeter range with a satellite. Basically, as I mentioned, we are going to go through three main blocks, three main topics, which are galaxy clusters, and I will talk a little bit about Sunyaev-Zeldovich effect, extragalactic sources and backgrounds, and the structure of the Milky Way in this domain, the millimeter domain. Planck is a huge collaboration. Along the history, I think there are more than 800 people involved in the collaboration, more than 50 scientific institutes in Europe, USA, and Canada. You have here basically I think probably not complete, but almost complete list of all the institutions participating. The IC is here in the list. So, basic facts. What is Planck? So, basically, Planck is an instrument, is a telescope with two instruments. One is the low-frequency instrument, which is covering the range between 30 and 70 gigahertz. For those of you which are used to think in terms of wavelengths, we are covering between 1 centimeter and 4.3 millimeters. And then we have another instrument, which is the high-frequency instrument, which is going from 100 to 800 gigahertz, which in wavelengths means from 3 millimeters to 350 microns. So you see that we are covering from the centimeter range to what we are usually calling the very far infrared, okay? From the point of view of optical astronomy. The angular resolution of these channels ranges from basically half a degree at 30 gigahertz at 1 centimeter and goes down to roughly 4 arc-minutes in the high frequency channel at 350 microns. And the sensitivity, especially the sensitivity in the channels that are going to be used for cosmology, to give you an idea of the improvement, is basically a factor of 10 better than the thing that you expect to do with WMAP in 8 years of observations. We already have the WMAP 7 years. So the sensitivity of Planck is basically a factor of 10, and this is a real number. I mean, I'm quoting now the sensitivities measured on flight. Okay, so basically these sensitivities that were specified when building the satellite has been confirmed. Planck is an extremely complicated instrument, basically because for the first time in space we are using a technology of active cooling. The cryogenic system of Planck is extremely complicated. As I said, the two instruments, the low-frequency instrument is working at 4 Kelvin, and the high-frequency instrument is working at 100 millikelvin. So we need a system which is actively cooling in space, and as I said, this is a thing that has been done for the first time in space. So, quick look to the two instruments. The low-frequency instrument, the PI is Italian, it's Reno Mandolesi from Bologna. Probably this is the instrument that you are more familiar with because the IEC, most of the participation of the participation of the IEC is going through this instrument, and I have to put one slide summarizing what is our contribution. So basically, we as an institute, we're producing the electronic box which is controlling the low-frequency instrument. So this electronic box which uses here, the nominal version and the flight version, is flying and is, has been working and is working very well according to specifications. So I think from that point of view, we can say that this is a success of the things that we have been doing here. We can do technology for space, and it's working very well. The other instrument, as I said, is the high-frequency instrument. Basically, you have a sketch here, and the PI of this instrument is Jean-Luc Bouillet from France. Okay, we already have a talk here at the IEC by Ismael on the results of Herschel. Probably you will remember that Planck and Herschel were launched together in 2009, and both of them were placed at 1.5 million kilometers from the Earth in the second Lagrangian point, which is a very convenient point from the point of view of observations because you can keep the solar emission basically far away from the field of view of the satellite all the time. Well, I start to flash now some of the results coming from that you can find in the list of papers that I was mentioning. You have here a sketch of the thermal performances of Planck, how the whole system is cooling basically from the end of May 2009, when a couple of weeks after the launch, and how it's reaching finally in the focal plane of the HFI the temperature of basically 100 millikelvin 2 months after this process is starting. So these are real data of the thermal performances. So in a single slide, what is the status of the satellite and the observations? So first thing to say, the instrument is very stable, as it's working very well according to the specifications. The sensitivities that we expected from ground measurements are confirmed. Second important thing to say is that if you compare to other space experiments like Herschel, for example, we are used to thinking experiments which are observatories looking to specific regions. Planck is not doing that. Planck is covering the whole sky. It's basically taking 6 months to do a complete coverage, and the nominal mission of Planck was 14 months. Okay, that nominal mission ended at the end of 2010, so we can say that we covered already the expectations, and we are even more than that because we basically double the expected nominal mission. So we have data roughly until January this year, which is basically a bit more than basically 4 and something, practically 5 surveys. So that means that from the point of view of taking the data, Planck has been already a success. The yes? The spinning rate of the satellite? I don't, do you have the number in mind? It's of the order of minutes. Okay, so the basic timeline, as I said, in January, the active cooling system for the HFI is starting to finish. And from the point of view of releases of data, we already have last year the papers that I'm going to talk now, but we will have 3 major milestones in the future that I think is important to keep in mind. Between now and June, we are going to release what we call the Planck intermediate papers, which are additional results which are not involving cosmology. Okay? In February next year, the collaboration is going to release the nominal mission data. So maps will be made publicly available. There will be new catalogs, legacy catalogs of point sources, and the cosmology papers will appear. And 1 year after that, we will basically have a similar release, but containing all the public data from Planck. Okay? So basically, cosmology in 1 year from now, and the final data in 2 years from now. This is an image that you have probably seen already of the Planck 1 year all-sky survey, and it's basically the image from which all the science that I'm going to describe is extracted. This image is a combined image of all the Planck channels in order to highlight the galactic emission. From this image, the CMB has been subtracted because no CMB science is included in this release. So if you look at this image, of course, these galactic coordinates, you start to identify some familiar regions. You have there, for example, the emission of the Large Magellanic Cloud. You can see Andromeda, Perseus, the galactic center. Some radio sources are obvious, 3C273. And you can also say a lot of things about the structure and the physics of the galaxy. There was a press release in July 2010 going together with this image in which you had a glimpse of what is the kind of science that Planck can do. Okay, so coming to the main topic of the talk, basically this is the special issue that I was mentioning, appeared in December last year, covering these 26 papers, and I'm going to try in the next minutes to give you an overview of basically the highlights of all this collection of papers. I tried to group all these papers into topics. Of course, you have the first papers describing the mission, the thermal performances, and so on. But if you group them in science topics, basically you have a list like that. So there are papers covering the study of galaxy clusters, papers studying the spectral energy distribution of radio sources, study of the dust emission in near-infrared galaxies. There is one paper dedicated to the characterization of the cosmic infrared background, another set of papers on the radial distribution of molecular neutral and ionized gas in the Milky Way, another set of papers on the physical properties of the ISM, basically the molecular clouds, and, well, a couple of more papers on new physical processes in the ISM, like, for example, the anomalous microwave emission that I will be mentioning later. So I think, well, I will not have time to cover all of them in detail. Basically, I want to flash 1 or 2 slides for some of the topics, just to give you an idea of what are the important results that Planck is covering. And at the end of the talk, I will devote basically 5 minutes to go into more detail of the first point, galaxy clusters, which is the field and that I know better. Okay? So basically, this is what Planck is producing. You have your 9 frequency maps with CMB subtracted. You have there the emission from the galaxy. In the low frequencies, you are basically dominated by synchrotron emission. In the high frequency, you are basically dominated by dust emission. If you do the combination of all these maps, you obtain the previous image of the press release. Okay, so first data product coming from the Planck collaboration. The first data product is what we call the early release compact source catalog. So what is this? So the idea was that Planck, after 1 year of operation, should release to the community a catalog which it should be designed for follow-up studies. This catalog is including basically 15,000 individual objects detected by Planck. Many of them were already known, but many of them are new. And indeed, there are people here that are working in the follow-up of these sources, for example, with Herschel. So this catalog is basically including radio sources, dusty sources, the sources that emit an infrared, and there are two specific catalogs which are also released with this big one. Which one is related to what we call the cold cores, that I will explain in a minute what is the meaning of this, and another specific catalog on galaxy clusters. All of these clusters, as I said, all of these catalogs, as I said, has been selected to be very high accuracy catalogs. So that means that we are using a very high signal-to-noise threshold. That means that the final legacy catalog from Planck will go much lower in sensitivity. But the idea was to release things which are very clearly objects, real objects, for follow-up observations of the community. So basically in this plot you have what is the flux density limit in the Planck frequencies. So you see that basically in 350 and 50 microns we are roughly at the level of 0.8 Jansky, and the sensitivity is going down around 1 millimeter to the level of 0.2, 0.3 millijansky. Jansky, so 200 millijansky. The important point is that Planck is covering a frequency range which was basically not very much explored in detail in the past. So these catalogs are providing full sky information on a frequency window which was basically unknown in the past. So in this movie you basically have an image of the distribution of all these objects, all the compact objects, and you can see the objects now separated into galactic sources and extragalactic ones. So galactic sources are expected mostly are clamped around the galactic plane, and the extragalactic sources, they are more or less evenly spaced, although you see clamps, for example, in the region of the Magellanic Clouds. And these extragalactic sources can be separated into infrared and radio sources. Okay, so as I said, the catalog is public, is open to the community for follow-ups. You can download it and use it. Okay, few results about this catalog. If you take the set of radio sources from this catalog and you plot the source count, basically the main result that we obtain with Planck is that the source counts are in good agreement with the theoretical expectations. So we had a model prior to the launch of the Planck satellite, the Sotti et al., which is basically describing the expected number of sources in radio. And this model is fitting very well the distribution of the number counts of sources that we are measuring in the low frequencies of Planck. However, if you go to the high frequencies, what we find, and this is a discovery of Planck, is that the standard model that we have to describe the number of sources is over-predicting the number of objects. So this is very good because that means that you need to correct the model and you need to include this additional information. But it's good from the point of view of CMB analysis because that means that the contamination of sources would be smaller at the frequencies where we are going to do the cosmology. So basically this model is, zoom in the solid line, is the expected population of radio sources, the number counts of sources, number of objects that you have in the vertical axis. You have the number, basically the number of objects as a function of flux. Yes, extragalactic. No. This is extragalactic. Yes. So basically, here is radio galaxies, low frequencies, and here is dusty galaxies. Okay. So the first case, galaxies which are detected in radio, and the second case, galaxies which are detected because of the infrared emission. Okay. Normally, these are objects which can go up to redshift of several. Okay. 1, 2. I was mentioning a specific catalog of cold cores. So what is a cold core from the point of view of Planck? Cold cores are basically compact clouds. So you think in terms of molecular clouds, regions where we are going to have star formation. So physically, these are regions with very low temperatures of the order of 10 Kelvin or so, sizes of the order of 1 megaparsec, and masses of the order of between 10 and 100 solar masses. So if you look here in the left, you have an example of the spectral energy distribution of a cold core. And you have here the explanation why these things are very difficult to detect in other wavelengths and why Planck is important to detect these objects. These things are so cold that the spectral energy distribution is peaking around 300 microns. So that means if you try to detect these things in the near infrared, or if you try to detect those things in the centimeter wavelength, you cannot see them. So you need something which is proving the region around 300 microns. You have here a map of this cold cores density. And as I said, this again is a public catalog, open for follow-up. And I think this catalog is offering very exciting prospects for the study of star formation. Okay, so the remaining catalog, which is the galaxy clusters, I will mention it in the last part of the talk. So what are the other results that I was mentioning from Planck in this release? Okay, one of the things that Planck is doing is characterizing the fluctuations in the cosmic infrared background. For those of you that don't know it, the cosmic infrared background is basically the integrated light coming from very high star-forming galaxies, very high redshift star-forming galaxies. The basic idea is that galaxies are redshift 2, 3, which are forming stars. These stars are emitting ultraviolet photons, and these photons are reprocessed by the dust and emitted in wavelengths which can be observed by Planck. So basically, taking into account the wavelength coverage of Planck, we can probe the range between redshift 2 and redshift 3. In this particular paper, we were studying 6 regions, high galactic latitudes, low contamination. And basically, if I have to highlight one of the main results, is that Planck is detecting the fluctuations in the cosmic infrared background, that the spectrum of those fluctuations is following what you expect, or what you measure. This is the measure from the COBE satellite for the cosmic infrared background, and these data points are the measurements of Planck for the fluctuations. Okay? So basically, we are following the same pattern of the total intensity, but for the fluctuations. And the fluctuations appear at the level of 15%. Okay, there are a number of papers in this release which are studying the properties of the dust. This is one very impressive image that was included in the press release of March in 2010, which is showing a region of basically 50 by 50 degrees. So this image is including a combination of the 2 high frequency channels of Planck and the 100 micron channel from IRAS. Basically, here you can see the temperature of the dust. So bright regions here are high temperatures. Low brightness regions, colored in red, are low temperatures of the order of 10, 12 kelvins. Okay? To give you an idea of the comparison of the resolutions, that region has been also observed by Herschel. So you can have an idea of how we can compare the 2 experiments. Before going into the details, I would like to put a general slide so we all understand what I'm talking about. When we measure dust emission in millimeter range, we are basically talking about the emission coming from big grains. So you are familiar with the emission from the dust in the near infrared, for example, which are dominated by the emission of very small grains, and you have also several lines there coming from, for example, polycyclic aromatic hydrocarbons. But the frequency range that Planck is covering is going, let's say, in the very far infrared, so basically millimeter range. And there, you basically have no lines. You have thermal emission from big grains. And this thermal emission is basically described by a simple law, which is a modified black body. So there are two parameters which are describing the dust properties: the temperature of the dust and the opacity. Okay, so Planck can measure these two properties. This is a map which is in the top left, a map of the distribution of temperatures of the dust obtained with Planck. And in the bottom you have the relative errors in percentage. The errors are going between 6 and 10% basically. And as you see, the temperatures ranges between 12 Kelvin and 50 Kelvin. There are basic general conclusions. For example, the center of the galaxy is having a larger temperature than the outer regions. And there are many things that you can learn from here, but I don't have time to enter into the details. The other property that I was mentioning is the opacity, which is basically giving us an idea of the column density of hydrogen. In some sense, this is related with extinction. Okay, so this is a map of the opacity of the dust at two frequencies, at 857 gigahertz. I remind you that this corresponds to 350 microns, and 100 gigahertz, which is basically of the order of the millimeter. Okay. So, thanks to these results, that we have a very precise description of the dust properties, Planck is, one of the highlights of the results of this release is the confirmation on, let's say also discovery, of a new component of the dust that we call the dark gas. So I will try to explain that in a slide. What is the meaning of dark gas? Basically, the optical depth of the dust is a measurement of the total column density of hydrogen along the line of sight. From radioastronomical probes, you can measure the column density of hydrogen in molecular state using the 21 centimeter line, which is what is described in the first equation. So basically, that is proportional to the antenna temperature in 21 centimeter. But you can also probe the molecular hydrogen, not directly by molecular hydrogen lines, but you need to use a tracer. And normally, the molecular hydrogen is not emitting in millimeter because, the molecule is diatomic and it has no dipole moment, so you don't have emission. So you need a molecule that is having a dipole moment, and this is the CO molecule. So you use carbon monoxide to trace the presence of molecular hydrogen. Okay, so if you represent the dust opacity as a function of the total column density, at very high densities, the CO is tracing very well the dust opacity. So that means that the CO is a very good tracer of the column density. At very low densities, neutral hydrogen is doing well, but at intermediate column densities, Planck is finding an excess with a very high significance that is showing that there is an excess of signal which is not traced either by the extrapolation of CO or molecular hydrogen. So this is what we call the dark gas. It's a component in the dust which is not traced either by 21 centimeter molecular hydrogen or, atomic hydrogen or molecular hydrogen. It's extremely interesting to see how is the distribution of these components in the interstellar medium. But I don't have much time to enter into the details. I just want to give you a quick a glimpse on what are the results, for example, in a star-forming region. You have here in the top left the Taurus region. Okay, So you have a region there where you have star formation. And first I'm showing dust temperature. So if you have star formation in the clouds where you have star formation, if stars are starting to form, that means that these clouds has been cooling and they should have low temperatures. So this is what you see. In the regions where you have the star formation, you see that the temperature is low, of the order of 10 Kelvin. If you plot the opacity, it's the other way around. These things are bright because the column density of hydrogen is very high. So what happens if you plot the dark gas? So what you find is that basically this dark gas is tracing the outskirts of these star-forming regions. And there are physical reasons for that. But, okay, I think I don't have much time to enter into the details. But, I mean, if you're interested, I invite you to ask or to go directly to the papers. So in order to close the overview on the physical emission processes from the galaxy, I would like to mention one process, the anomalous microwave emission, that from the historical perspective, from a historical point of view, is something very special for the CMB group here at the IAC, because we started to work 10 years ago already on this topic. And one of the first measurements of the discovery of one of the first measurements on the system of this anomalous microwave emission was coming from the Tenerife experiment, and later was measured in more detail by Cosmosomas. Anomalous microwave emission is basically an emission in the microwaves, which is peaking around 1 centimeter, which is especially correlated with the dust, but that you cannot interpret as an extrapolation of thermal dust to the centimeter range. So the prototypical example is the Perseus molecular cloud. So you have here, in the Perseus molecular cloud, the emission of thermal dust, and this is the extrapolation that you expect from thermal dust, and you find that in the centimeters there is an excess of emission. Okay? These data points in this plot in green are coming from Cosmosomas, and in the case of the red ones are coming from WMAP. Okay, so Planck has been studying in detail the anomalous microwave emission, and the basic conclusion is that Planck is confirming the existence of this anomalous microwave emission as a new emission process in the galaxy. Yes, it's completely different because the dark gas is something which is related to the dust emission at very high frequencies. I was showing results at 350 microns. And this anomalous microwave emission is in the centimeter range. So it's easy to see in this distribution. So the dark gas is something that you see here, and the anomalous emission you see here. The problem is that we are always using these names of anomalous emission, dark gas, and we are using always the same names, and it's easy to confuse. But they're physically different things, okay? Anomalous microwave emission is an excess of emission with respect to the extrapolated emission of the thermal dust. Yes, there is one result. I mean, there is one result in one external galaxy which is showing this presence. What Planck is showing is that in our galaxy is something which is common. I mean, this is a map which is trying to trace the presence of anomalous microwave emission, taking the 30 gigahertz, the 1 centimeter map, and removing the contribution of the extrapolation of the dust and removing the contribution from synchrotron. So basically, this is what you have. And in this map, you can see regions, for example, the Perseus molecular cloud, which was the one measured by Cosmosomas, but many other regions. I mean, it seems that this is a physical mechanism which is there, is spatially correlated with the dust. So that means that you have more emission in the galactic plane, but you can have also regions of high galactic latitude. Planck, for example, is providing very detailed maps. This is the case of the Perseus molecular cloud in the complete range of frequencies. And here, for completeness, we are including the 1.4 gigahertz map and H-alpha emission in order to characterize the free in that region. So basically, this is the update when you include the Planck data points, which are coming in red. So you have the Cosmosomas data points here, low frequency, in blue the WMAP, and Planck is tracing very, very well the thermal dust component. If you correct for that thermal dust component and for the free emission, you have basically this excess of emission, which is fitted very well, but by a model, theoretical model of emission, which is called spinning dust. So what we think now, it is the anomalous microwave emission. Basically, what we think is that it corresponds to emission of dust grains with a small dipole moment which are rotating. Okay, so it's basically rotational emission from dust. The total in intensity is relevant at low frequencies. At 30 gigahertz, it could be comparable, or I mean, not to the synchrotron, but following the synchrotron probably will be the second relevant contamination. But this is something that is peaking around 20, 30 gigahertz. So if you go to the cosmological channels, it's disappearing. But in the case of Cosmosomas, at 10 gigahertz is the dominant emission. In the Cosmosomas map, this was the dominant emission. Okay, so the last few minutes of the talk, I would like to focus on the results of galaxy clusters from Planck. Basically, in this release, we are including 5 papers, which are covering different aspects of galaxy clusters. And before going to the details, I would like to flash you a couple of slides about giving a context of what are galaxy clusters from the point of view of Planck studies or from the point of view of cosmology. For most of you, this is an image of coma in 3 different wavelengths. Okay. For most of you, when I say galaxy cluster and I say coma, you think in the left image. Okay. You see the distribution of galaxies. So what I'm going to talk in the next slides is something more related to the second and third image. Galaxy cluster, from the point of view of mass, is basically hot gas. If you take into account the amount of baryons that you have in the clusters, galaxies represent a small fraction compared to the gas that you can see, for example, in X-rays. This gas we understand that is produced during the process of formation of the galaxy cluster. Shocks are hitting the gas and reaching temperatures of the order of 10 million kelvins. 10 million kelvins produce Breststralung emission that you can see in the X-rays. And this ionized gas is also distorting the CMB, and I will explain in a minute what is the Sunyaev-Zeldovich effect, which is basically the tool that we are using to trace galaxy clusters. Why is it important to observe galaxy clusters? The final objective is to do cosmology, and you can do cosmology in many ways. Clusters, I'm going to read the other way from bottom up the slide. Clusters are first samples of the universe in the sense that the fraction of gas to the total mass is a good representation of the universal fraction. So you can use galaxy clusters to measure omega baryon and omega matter, basically. You can use also galaxy clusters to, for example, obtain the Hubble constant. If you combine Sunyaev-Zeldovich effect and X-ray images, Sunyaev-Zeldovich effect is something which is not going to depend on redshift, and X-ray images do depend. You can obtain a measurement of the distance to the object, and then you can infer the Hubble constant. But probably the most important point, and is the message that I would like that you keep in mind, is that there is a lot of cosmology that you can do with the number, counting galaxy clusters, with the number counts. If you represent the number of galaxy clusters as a function of redshift, that function is very sensitive to the cosmology. Okay, so if you're able to measure with high precision that function, then you can infer constraints on the cosmological parameters. However, there is a practical issue which makes this thing very complicated in practice. In the vertical axis, you have to represent number of objects per unit volume, basically. So you need a methodology to detect the galaxy clusters in a uniform way. Okay, so you need to characterize very well what is the selection function of the survey that you are doing in order to do galaxy clusters. So it's not enough to say, I take all the galaxy clusters that I find in the literature. No, you need, in order to do the comparison with the cosmology, to select clusters in a uniform way. And this is a key point in which Planck is very important. But not only Planck, I'm showing here the results of the constraints on cosmology coming from Chandra. So you see there two subsamples of clusters, one around redshift center around 0.1 and another at high redshift above 0.35. And with the combination of these two number counts, you can infer constraints, for example, in the dark energy and in the amount of dark energy and the equation of state of the dark energy. So these kind of things is what we want to do with Planck in 1 year from now. Okay, so how we measure clusters using Planck? Basically, we use the Sunyaev-Zeldovich effect, which is a distortion of the CMB along the line of size of clusters. When we look to a galaxy cluster at frequencies of 270 gigahertz, we basically see no effect. If we look at frequencies below that, we see a hole. And if we look at frequencies above that, we see a bright source. Okay? So this behavior is unique and allows to trace very well galaxy clusters. The basic idea of the Sunyaev-Zeldovich effect and why it's important for cosmology is that the effect is independent of redshift. So that means that you can detect galaxy clusters at any redshift, provided that you have angular resolution, of course. I mean, if your cluster is like this and your beam is this, you are diluting. But if you have the proper beam, the proper angular resolution, you will have the detection. Okay, so what are the results coming from Planck? So I was mentioning in the early release there was a special catalog of galaxy clusters coming from Planck. This catalog makes use of the uniqueness of Planck for studies of galaxy clusters. Why Planck is unique? First thing is Planck is all-sky survey. If you try to remember what is the last all-sky survey which is looking for galaxy clusters, the last one before Planck was Rosat in 92. So after Rosat, there was no experiment doing a uniform and complete search in the whole sky of galaxy clusters. The frequencies of Planck are matching very well the spectral energy distribution of the Sunyaev-Zeldovich effect. We have a frequency at the zero, and then we have a lot of frequencies below and few frequencies above. So that's very useful to do the detection. In the case of the release of papers that I'm discussing today, the collaboration included a catalog of early what we call the earliest set sample. Again, this is a catalog containing very high reliability objects, signal to noise greater than 6 and purity greater than 95%. In the final legacy catalog that we will publish 1 year from now, there will be many more objects. But basically, again, the idea was to publish this first catalog to give a glance of what is the idea of what we can do with Planck. Okay, so basically in that early catalog there are 189 candidates. Most of them were known, but there were 20 candidates which were unknown, and many of them has been confirmed by a significant effort that has been undertaken inside the Planck collaboration. You have here the representation of what are the distribution of the galaxy clusters seen by Planck and how Planck sees them. And I have here a couple of slides showing, this effort of follow-up that we have been following inside the collaboration. We had follow-up in the X-rays, and you have here a gallery of images of X-ray clusters observed by XMM Newton. This is one of the papers included in the release. And if I have to highlight something, I will say that Planck allows to detect high redshift objects, which is the case of the lower panel. This is an object practical redshift 1, detected by Planck. And it's also possible to detect complicated systems. In the top, you see a supercluster detected by Planck that when it was confirmed, you can see in the left the signal from Planck, which is showing Sunyaev-Zeldovich effect, and in the right, when you go to the X-rays, you see 3 clumps. So it's basically a complex system in interaction. There is also a huge effort in trying to do optical validation and searching for the optical counterparts of these galaxy clusters. A part of that effort is undertaken here at the IC. And for example, I'm showing one of the galaxy clusters that was included in the release. This is an image taken with the IC80, and you can see there the color composite using the 3 Sloan filters, and in the contours are the distribution of the emission coming from the X-rays, and you can see there the red galaxies. The photoresist estimate that we obtain is very well consistent with the resist estimate that you can have, for example, observing iron line in the cluster with XMM. So, if you represent the distribution of masses of this object in the early release set sample versus redshift, the basic message, these are the data points from Planck, those in black. The basic message is that at a given redshift, Planck is detecting the objects which are at higher mass. Okay, so Planck is a very efficient instrument to detect at a given redshift very high mass objects. And this is my last slide. You can not only do studies of individual objects, but you can also try to do studies of combined objects by doing stacking. And this was a very interesting result because based on WMAP data, there was a controversy saying that it seemed that there were some variants which were inconsistent between the picture that you have in SZ and the picture that you have in X-rays. So basically what we did here is take a catalog of X-ray selected clusters for which we have X-ray luminosities, and from the X-ray luminosity you basically can predict the amount of gas that you expect to see. Then you can go to Planck, measure the actual stacking in those clusters. You can measure the Sunyaev-Zeldovich effect, which is basically proportional to the amount of gas, and you can compare the two things. So what you see there in red are the measurements from Planck, and in blue is the prediction of what you expect. You have all the data points there. Each point corresponds to a galaxy cluster, but in blue you have the average of the prediction. So the basic message is that it's a very good agreement, a perfect agreement between the prediction from the X-rays and the prediction and the measurement from the Sunyaev-Zeldovich effect. Okay, so basically I've finished here. In summary, Planck has been working flawlessly and without interruption since we started the survey in mid-August 2009. The high-frequency instrument finished its operation last January, and we are now well into the 5th Earth Sky survey with the low-frequency instrument that will continue during part of this year. And I hope that I convince you that although Planck is designed for cosmology, you can also cover a wide range of astrophysical topics, going from cosmic infrared background, properties of the interstellar medium. You can study galaxy clusters. And I hope also that I showed you that the data results which are already coming from Planck are highlighting the high quality of the data and the very good performances of the satellite. And just to finish saying that in early next year, early 2013, by January, February, we will release the maps of the nominal mission, full maps, including the CMB, the first cosmological results, and the legacy catalogs, now including sources, clusters, concourse, everything to lower signal-to-noise thresholds. So stay tuned. Thank you.
Thank you very much, Jose. Now, we only have time for a few quick questions here. There will be coffee and cakes down in the library afterwards if you have additional questions. But does anyone have a question? course, not Joe.
I have many questions because you have mentioned, but okay. So my first question is in relation to the galaxy clusters. You said that the only limitation that you could have is the resolution of your instrument. So in this sense, the resolution of Planck is enough for going up to the very high redshift, or you lose some clusters above some given redshift. So this is my first question. My second question is related to the dust distribution, because in some of your slides, the distribution was very weird to me, in the sense that I was expecting to see most of the distribution of dust in the plane of the galaxy, and however, for some slides, it appears more vertically than horizontally. So if you can expand in these two questions. Thank you.
Okay. So first question, number of galaxy clusters. Yes, there is an issue with the resolution. The average size of a galaxy cluster, if you plot an histogram of the distribution of the virial radii of galaxy clusters, that distribution is peaking around 1 arc-minute. So that means if Planck is having a resolution of 4 or 5 arc-minutes in the channels that we are using for detecting the clusters, that means that yes, we are losing, because of the resolution, there are objects which are faint, which will not be detected. But I want to emphasize again that the point is that with Planck you can do full sky, that you cannot do with other experiments that can go very deep, matching better angular resolution, but not the full sky. And the second thing is that you can have a uniform selection of clusters across the whole sky, which is critical in order to do the cosmology. Otherwise, you cannot do it. And the second question concerning, for example, here, the distribution of dust. Okay, maybe in this color scale, okay, keep in mind that CMB is not included there. Okay, and that this color plot is showing basically dust temperature. So in that sense, this color scale is highlighting a lot the emission at high galactic latitudes. In any case, there are many structures which are familiar. You can see there the North Galactic Spur, which is here, which is basically a local structure that is very bright in synchrotron, and you have also emission in dust. So you expect at very high galactic latitudes.
So what is the physical mechanism explaining such a high temperature at such latitude?
It's local structure. It's a local structure.
But where is it coming from? So what is it? So because in the plane of the galaxy, it's easy to understand. So you have a lot of supernovae.
Basically, the spur in the maybe it's better if I go to the frequency map. No. This well, maybe it's not easy in here, but this spur, which is going to very high galactic latitudes, is a supernova remnant which is very close to us, and because of the subtended angle is very high, you see in projection up to very high galactic latitude.
Okay, one more question if the microphones will behave.
Yeah, when you were showing this plot where you were comparing for extragalactic sources, and there was a plot comparing the model with the observation, and I agree that for higher, I think it was sensibilities, there was a very good agreement, but then there was a drop there at the middle of the plot, more or less, there was a drop.
Well, yes,
I guess that's because of the sensibility of the instrument.
It's completeness, yes.
Yes, but then are you expecting really a big drop, fewer sources, or those points are completely unreliable?
This is coming from the completeness of the instrument. When you are reaching the confusion limit, you start to lose sources, basically. So, I mean, the data points which are okay. So basically, the range in which you have reliability. Remember that I was mentioning completeness down to of the order of 0.8 Jansky. So 0.8 Jansky is around there. Okay, so the rest of the data points is completeness.
Well, let's thank Jose one more time for his very informative talk. And please remember the Café Scientifico down in the library. Free coffee and cakes and whatnot, so no reason not to go.